Let's consider a completely new category of problems here, swinging problems. Every time when you have a bob attached to a string or a rope and it swings back and forth, most of the times the questions are solved actually very nicely through energy. Here's our example. You watch a swinging pendulum and you notice that the little bob has a speed of 3.0 meters per second at its lowest position. How high above the lowest position does the pendulum swing? Since we'll be considering energy here, we will need to start with marking our ground so we know where the gravitational potential energy will be zero. A natural choice will be the lowest position of the pendulum, so that the total mechanical energy there will be kinetic plus potential equal to 1/2 mv squared plus mgh. Here the lowest position, the speed will be the speed at the bottom, which the problem tells us is 3.0 meters per second, and mgh at the bottom will be actually 0 by virtue of our choice. That's how we chose our ground. So we consider the total mechanical energy at that location will be simply whatever we have in the form of kinetic, 1/2 mv squared. At the other location where we're height h above the lowest position, the total mechanical energy being kinetic plus potential will be 1/2 mv squared plus mgh. Of course, that is a turning point. This is where the location where the bob stops momentarily and then starts swinging backwards. So we know that the speed there will be 0, and so the total mechanical energy will be equal to whatever we have in the form of potential energy, mgh. Usually here I set up the conservation of energy principle, but I want to consider a subtle element here in this problem. Let's start with the work-energy relation first, or theorem, which sets that any changes in the mechanical energies will always be due to the work of the non-conservative forces. Technically here we do have a non-conservative force. Remember, the non-conservative forces were simply speaking, all the forces except for gravity and elastic force of a spring, at least in mechanics. So this work-energy relation will give us that the difference between the mechanical energy at the top location and the bottom location has to be equal to the work done by the tension in the rope here, because that is the force that is neither gravity or elastic force of a spring, but it's there, present and applied to the bob. So let's consider some intermediate position of the bob, and we know that the tension in the rope or the string will always be along that string towards the center of the circle, or towards the top. At the same time, for a very small minute time interval, let's say we consider a very small displacement of the ball, delta L, and that delta L will be along the tangent of the trajectory. In this case will be along the tangent of the circular arc. As the bob swings up or down, both tension and the vector for the displacement will be actually rotating together with the bob. The important thing here, however, is that the angle between the two vectors will always remain equal to 90 degrees, because tension will always be in the radial direction of the circle and delta L will always be in the tangential direction of the circle. And here we'll need to review the definition of work in a very simple way, without worrying about variable forces and changing angles. In a very simple way, when we have a force that remains constant and it's applied at a particular direction, we have that the work of that force will be equal to the force times the displacement times cosine of the angle between the two vectors. Now the vectors change the position, but the important thing is that the angle between each other remains always equal to cosine 90, so it allows us to use the simplified formula. And we can also see that at any given instant the work of the tension will always be 0. So yes, we do have a non-conservative force here, but it doesn't do any work. In other words, the difference between the energy at the top and the bottom will always be 0, and that is why we always actually talk about conservation of energy. And in fact, many problems will just skip that little subtle argument here and jump directly to the conservation of energy principle that will stipulate that the energy at the top will be equal to the energy at the bottom. In other words, At the top, remember, we'll have mgh as a total mechanical energy, and at the bottom we have 1/2 mv squared, where v here is the speed at the lowest location given by the problem to be 3.0 meters per second. The mass will cancel, and so here we can see that the height, how high the pendulum will swing relative to the lowest position, will be 0.459 meters. Notice here that the mass cancels out, so a lot of swinging questions will frequently actually skip the mass of the pendulum and will not give us what the mass is, because the mass cancels out in the end.